Okay, so hopefully you took a couple of seconds to do this while you were switching videos, but this next one we'll go over these answers. Sorry about that blue thing. The next one is a negative out in front, which means something out in front that's not with your x is going to affect your y values. So that's going to be a vertical reflection or a vertical flip. You can say flip or reflection, I don't care. This negative is technically out in front, so we're going to call that a vertical reflection as well, or vertical flip. And this one is on the inside, which really, in this case, for the cubic function, if you reflect it horizontally or vertically, it will be the exact same transformation, because this is the same as negative x cubed. So it doesn't matter which one you put here, either vertical or a horizontal reflection or a flip. Technically, the way it's drawn, I would say a horizontal, the way it's written. Then in part E, a 1/2 that is out in front. Technically, it's out in front. It would only be inside if there were parentheses around it. So this 1/2 that is out in front is going to be a vertical, and it's not with the x, it's out in front, so it's not lying, it's telling the truth. If you multiply something by 1/2, that is going to make it smaller. So there's going to be a vertical compression by a factor of 1/2. This 2 that's inside with your x on part F is going to affect it horizontally, so I know it's going to be a horizontal something. Horizontal, and then you would think that it would be multiplied by 2, that would make something bigger, but it's with the x, so it's lying, so it's really being divided by 2. So it's a horizontal compression, really like by a factor of the reciprocal of that, so by a factor of 1/2. And then on this part G, the parent function here, so this 2 is part of the parent function. The parent function is really y equals 2 to the x. So the transformation is the 3. And that's inside with your x, so it's lying, so it's similar to part F. It's a horizontal compression by a factor of 1/3. So you always take the reciprocal when you're doing the horizontal, whether it's a stretch or compression. So in this part H, this one will be what I'm trying to talk about. So x over 4 is really the same as the absolute value of 1/4 x. So that 1/4 is inside with our x. 1/4, if we multiplied something by 1/4, usually that would make it smaller. However, x is lie, so it is making it bigger. So this is really a horizontal stretch. And instead of saying a horizontal stretch by 1/4, it's a horizontal stretch by whatever the reciprocal of that is, so by 4. So hopefully that kind of gives you a couple examples of stretching and compressing and reflections. I think that the shifts are really easy to see when they're inside or outside your function, so maybe we'll do a couple of graphing ones for that. So, well, yeah, let's just keep doing this. So describe the transformations. We'll do a couple of these. So describe the transformations. I'm not actually going to graph it yet. So our first example, we'll say this. Excuse me. Y equals negative square root of x minus 4 all over 3. So this all over 3 thing, I would rewrite this as negative 1/3 times the square root of x minus 4. That way it's a little easier to see what the transformations are. So the transformations, we have this as a transformation, this is a transformation, and this is a transformation. So we have 3 transformations. Our parent function is the square root of x. So the negative out in front is going to be a vertical reflection. And then the 1/3 is going to be a vertical, and since it's vertical, it's not lying, it's telling the truth. So that would be making it smaller, vertical compression by a factor of 1/3. And then the minus 4 is inside with your left, inside with your x. You would think that it would move to the left 4 because minus 4 on the x-axis would go to the left, but it's a liar. So that would be technically how you would say it would be like a horizontal shift or horizontal translation to the right 4, but you can just list right 4. So those would be the 3 transformations on that. We'll do a few more of these and then a couple graphing ones, and then that will pretty much be it. So another one of these would be y equals, sorry, it's about right now. Y equals 1 over x minus 4 plus 5. So if you want to identify what the parent function is, that wouldn't be a bad idea. Parent function in this case is going to be that rational function of y equals 1 over x. So a couple things have happened. Only two things have happened. It's been shifted to the right 4. That's what that's doing. And it has been shifted up 5. That's what the 5 is doing. So there's the two transformations on that one. Another example, just to give you a few, would be y equals 2 times 2 to the x plus 3. So the parent function here, whatever the base is part of the parent function in an exponential graph. So exponentials have an unlimited number of parent functions. So we'll say y equals 2 to the x is that parent function. So the 2 out in front is going to be a vertical stretch by a factor of 2, and the plus 3 is going to move it to the left 3 because x is lying, it's up with our x. Okay, then we'll do 2 graphing functions, and then we'll be done. So we want to write an equation. So this example, write an equation to represent the transformed function. So you would be given this graph. So we have a graph, and it is down here, and down here, and down here. So it looks like this. So what you need to know is you need to be as familiar with your parent function as possible so that you know what function that is. So that parent function is really a y equals square root of x, and it's been transformed. So the parent function is up here. So hopefully you can see that that has been reflected across across both axes. So it's been reflected down and then reflected over. That's how it's getting that shape. I don't know if you kind of followed me there. So it has a negative on the inside and the outside. So when I'm building my function, I'm going to have negative, I don't know if there's anything else in there, and then a negative x. Okay, so in addition to a negative on the inside and on the outside, it has been shifted to the left 1, 2, 3. So left 3, technically this negative would be like on the outside of this, so left 3 would be plus 3 right here. And if you look at the points, it goes over 1, down 1. There's no vertical stretch or horizontal compression or anything like that. So this is pretty much what our function is right here. To make it look a little prettier, you could simplify it and change it from graphing form just to regular form. So that'd be a negative square root of, and then if I distribute my negative here, it'd be negative x minus 3. So that would be what that would look like. So you kind of have to just use your knowledge of the parent function and see how that's been transformed. Okay, then our last example we'll do is to write an equation. Oh wait, let's graph this. So let's graph y equals 3 times the absolute value of x minus 7 plus 4. So the parent function on that is y equals x, or y equals the absolute value of x. I don't know what's wrong with my board. So it goes through 1, 1, negative 1, 1, and it looks like that. That's the parent function, is y equals the absolute value of x. So this transformed function has a vertical stretch of 3. It has been shifted to the right 7, and it has also been shifted up 4. So you can do this on the graph just visually. A vertical stretch of 3 would multiply your y values by 3, so that would change it 0, 0, and then instead of going up 1 and over 1, it would go up 3 and over 1. So it's going to make it steeper like this. And then from there, you could just move it to the right 7 and up 4. That would be pretty simple to do. right 7, so 1, 2, 3, 4, 5, 6, 7, and then up 4 would go up 1, 2, 3, 4. So it'd be up here and be that kind of steep graph like that. So this blue one is our transformed function. You could also do it with your parent function points. So let's say we have x, y. Our parent function points for this, we'll say are negative 1, 1, 0, 0, and 1, 1. So if we look at these in terms of the points, the vertical stretch of 3, this is what I meant by doing these ones first. The vertical stretch by 3 is going to multiply our y values by 3. So 1 times 3 would make our new y value 3. 0 times 3 would make it 0. And 1 times 3 would make that 3. So that would be the new y values. But then the other vertical transformation is up 4. So up 4 means that we would really add 4 to all of these. So 3 plus 4 would give us 7. 0 plus 4 would give us 4. And 3 plus 4 would give us 7. So really, those are our new parent function, well not parent function, transform function points. And then to affect our x values, going right 7 means that we would add 7. So it would be our x values plus 7. So if I add 7 to all these, that would give me 6. Add 7 to 0, that would give me 7. Add 7 to 1, that would give me 8. So there are my new values. I could use 6, 7, which is over 6 and up 7, which would be right here. 7, 4, which would be right here. And 8, 7, which would be up here. So you could use those points or you can graph it by transformations. It doesn't really matter which one.